So folks, in our last video, we mentioned that the series, the sum from n equals 1 to infinity of 1 over n squared, converges and happens to converge to the sum pi squared over 6. This is actually, I feel like, one of the rare examples that we get in a series discussion where we actually know what the sum of the series is, and it's written explicitly like this. There are a few others, such as geometric series. We can actually give the explicit formula for it. But in general, when given just any old series, the series from n equals 1 to infinity of b sub n, we won't be able to, before we'd even try to ask the question, what value does it converge to, we just want to ask the question, does it converge? And this is an important thing to keep in mind. For example, if b sub n is the sequence 1 over n, if I start writing out the terms of this, we would have, this would be 1 over 1 plus 1 over 2 plus 1 over 3 plus dot dot dot, plus here we'd have, say, 1 over j plus dot dot dot. And if I were to add up, so remember that really what we're doing when we're talking about an infinite series is a limit of a sequence of partial sums. If I were to add up, say, the first 1,000 terms of this series, the first 1,000 terms of this series, I would get this, approximately 7.485 if I were to add up these first 1,000 terms. Let's continue that. So here you can see I've added up the first 1 million terms of this series, and I got 14.39. I added up the first billion terms and the first trillion terms. And notice this doesn't seem to be growing all that quickly. So the question that we want to ask in this case is, how come this series converges to a finite number? In this case, we're actually able to find that finite number. How come this series converges to a finite number where, well, this series right here, what we would say is that it diverges? Okay. Notice that in both cases, if we were to take the limit as n approaches infinity of 1 over n squared, that limit is 0. And if we were to take the limit as n approaches infinity of 1 over n, that limit is 0. In both cases, the size of the values that we add further and further out in the series gets smaller and smaller, approaching 0. But the key thing is that these values are approaching 0 fast enough so that the sum eventually converges. Whereas these values, although they're approaching 0 as well, they do not approach 0 fast enough so that this sum ever converges. And you can see that. I've added a trillion terms, and if I continue on, I would never get convergence for this. And I don't think it's readily apparent what makes this series converge and this series diverge. So now what I'd like to do is segue back to our document. And here we get our summaries of tests for convergence. So hopefully you learned each of these in Calc 2, but I want to give you a quick recap of them. The most important test to always do on any series is to confirm that the limit of the sequence goes to 0. Because, as we saw in our previous example, if the limit doesn't go to 0, then of course we're never going to get a finite sum because we're always adding on a non-zero number. And so it doesn't even make sense to ask the question, do we have convergence, if the limit of the sequence doesn't approach 0. So that's our test for divergence. And what I want to add here is a warning. This test doesn't say when a series converges. It only tells you it diverges. And the example that you want to keep in mind is this example here, where this series has a sequence that goes to 0 eventually. As n gets large, I'm basically adding on an arbitrarily small term onto my series, and we have convergence. But this series right here also has a sequence that converges to 0. I'm eventually adding up very, very small numbers to this series, but we still have divergence. After that, what we get in Calc 2 is a kind of a smorgasbord of different convergence tests. And these were all of varying degrees of importance throughout Calc 2. And I would say that in dealing with power series, the most common one that we will use is this ratio test. So I'm highlighting that to you now. And we will discuss it when we get to our first example of finding whether or not a series converges in our power series discussion. I've labeled, I think what I have here is a nice summary, and I'll let you read through this summary of convergence. And then what I'd like to do is in the next video, we will actually determine whether or not various series converge. So hopefully this was a sort of a refresher of what we mean by series convergence. And what we mean by that is whether or not as that upper limit, that stopping value of our sum goes to infinity, does our series arrive at a finite number, even if we can't specify what that finite number is? Or do we just keep adding on more numbers and we never arrive at any finite value? Folks, I know this is in no way an appropriate coverage of the topic of convergence, but it is just meant to be a review. All right, I'll see you in the next video where we actually find the key, whether or not these series down here converge.